Hello and welcome to today's physics class. This is a continuation of our physics learning support program. I'll implore you to please subscribe to this channel so that you can get notified as new physics videos are added, and also make use of the videos already on the channel to learn different topics in physics. So today we'll be looking at equilibrium of forces. This is one in a series of videos that address this topic. There are a couple of videos already that addressed a topic of equilibrium in different aspects. There is a video on this channel that talks about the triangle of forces, which is how we deal with forces, three non-parallel coplanar forces that keep an object in equilibrium. So you may want to see that video to be able to learn more about coplanar forces that are non-parallel. Today we are going to be looking at equilibrium of forces. This lesson is going to focus more on the types of equilibrium that we have and stability of objects. The objectives for this lesson will include explaining the concept of equilibrium, mentioning the types of equilibrium, and of course explaining what each of them means, explain the concept of coplanar forces. We will also be defining the center of mass and center of gravity of objects, and then we'll also explain stability of objects. So let's get started by looking at what equilibrium means. In physics, the term equilibrium refers to a scenario where an object is not accelerating. We describe an object that is not accelerating as being in equilibrium. Please note the use of the terms here. The term is not accelerating. That an object is moving does not necessarily mean that it is accelerating. An object that is moving with a constant speed is not accelerating, so it is in equilibrium. Many a times we tend to think that objects are in equilibrium only when they are not moving. That is not correct. Whereas it is true that an object that is at rest, that is not moving, is in equilibrium, it's also true that an object moving in a straight line with constant speed is in equilibrium. So also is an object rotating with a constant angular velocity. So the key thing is that once an object is not accelerating, which implies that there is no net force, no unbalanced or what you will call a resultant force on the object, then the object is at equilibrium. You remember our equation for force is mass times acceleration. If there is no net force on an object, if there is no unbalanced force on an object, then the force will be zero. The force in the equation F equals ma will be zero. If the force is zero, then it implies that the acceleration must have been zero, because we already know that an object will always have a mass. So the mass cannot be zero. But what would have made the force to be zero is the acceleration being zero. And irrespective of the size of the mass, once the acceleration of an object is zero, then the unbalanced force on it is zero. Now, I have to also explain that an unbalanced force being zero does not mean that there are no forces acting on the object. That an object has no resultant force or no net force does not imply that there are no forces on it at all. What that simply means is that the forces acting on the object act in such a manner that they balance each other out. So if the forward force or the moving force on an object is equal to the resisting force, such as air resistance or friction, if both forces are equal, then they balance out. So even though in that scenario there are two forces on the object, there's a force pushing the object forward, there's a force resisting the motion of the object in the opposite direction, Once the two objects have equal magnitudes, they balance out, and then we say the object has no net force. And that kind of object is said to be in equilibrium. We have two types of equilibrium. We have static equilibrium and we have dynamic equilibrium. I already explained each of them earlier, but for emphasis, an object is in static equilibrium when it is not moving. That means that the force that should have set the object in motion is being nullified by a force that is resisting the motion, and then the object remains at rest. So it is in static equilibrium. But if an object is in motion, but it is not accelerating, meaning that it is in motion but its speed is constant or its angular velocity is constant, then it is in dynamic equilibrium. Examples are the cars moving straight along the highway at a constant speed, or an object moving around in circles with a constant angular velocity. Now let's look at the concept of the center of mass. Every object has a mass. I said that earlier, that every object has a mass. The things that we treat as not having masses are things like particles, like very tiny particles of dust particles, things like that. We treat them as being without a mass. But by and large, every object that we have has a mass. You would remember that there is this concept that we were taught in junior school science about matter, and matter was defined as anything that has a mass and occupies a space. So when you talk of matter, talking of objects, different kind of objects, they have a mass. Now, by virtue of the fact that every object has a mass, then it implies that every object should have a weight. I said should because there are instances where the mass may not really have a weight. For instance, if a mass is in an empty space, is in a space that has no gravitational influence, no gravitational field, then the object will not have a weight, even though it will still have a mass. I also have to say here that the fact that an object does not have a gravitational field around it does not mean that its weight is equal to its mass. Many a times we think that if an object is in space, then its mass is equal to its weight. No. If an object is in space, if an object is in a region where there is no gravitational field, then it has no weight at all. Not that the weight is the mass. No, there is no weight at all. Because the formula for weight is mass times acceleration due to gravity. And where there is no gravity, then there cannot be an acceleration due to gravity. That means that the g will be 0. And once your g is 0, 0 multiplied by any mass will give us a weight of 0. Having said that, every object has a point at which its mass appears to be concentrated. So if you try to lift up any object, say a rod, a chair, there will be a point on that object where if you lift it at that point, it is easier to lift, so to speak. But if you try to lift it at some other point, it may be difficult. The object may be dragging along the floor, may be difficult for you to carry. So it's easier to carry an object from its center of mass, because that's where the weight of the object is concentrated. And once you're able to lift that part up, you're able to lift the object up. So every object has that point where its mass appears to be concentrated. That is what we call the center of mass. Now, the center of mass is the point at which the mass of a body appears to be concentrated. Note the keywords, center of mass. That goes with mass of a body. Word of caution. do not define the center of mass as the point at which the weight of a body appears to be concentrated. Once you attach weight to center of mass, it implies that you are not able to tell the difference between weight and mass, which is not good. So center of mass goes with the word mass, with the quantity mass. So center of mass is a point at which the mass of a body appears to be concentrated. Just as we have the center of mass, we also have a part or a point on an object called the center of gravity. As I said earlier, every object has a mass. When the object is put in a gravitational field, it has a weight. The weight of an object is the force exerted by the gravitational field of an astronomical body, such as the Earth, on that object. Now, weight is a force. Weight is a vector quantity, so it has direction. And the direction is that it always acts downwards, because every object accelerates towards the center of the Earth. So the arrow, which we use to describe the vector quantity weight, always acts downwards. Now, the point is, from what point on that object will the arrow start? An arrow acting downwards has to start from somewhere on the object. Now, the point where the arrow starts is the center of gravity of that object. So, every object, irrespective of shape and size, has a point where if you place that object on a pivot at that point, the weight of that object will be supported. So that total weight will be supported. The object will not tilt to the left or tilt to the right. It will just balance on the pivot. At that, once you're able to locate that point is the center of gravity of that object. We'll be looking at how to locate such points for different objects shortly. But important to note, the center of gravity is a point on an object where the weight of the object appears to be concentrated. It is from this point that the arrow that describes the weight, the vector weight of that object, begins to act or takes off from. Usually, the center of mass and the center of gravity coincide at the same point. But for really large objects, they will not be at the same point. But for smaller objects, yes, they coincide at the same point. Now note, as I said earlier, that the center of mass is used to describe the point where the mass appears to concentrate. Now, center of gravity is used to describe the point where the weight of the body appears to concentrate. Center of gravity is therefore the point through which the line of action of the weight of the body always passes, regardless of the position of the body. So, whether the object is lying down or a human being lying down or standing upright, the center of gravity will always be at the same point on that person or on that object, and it will always act downwards. The arrow describing that weight will always act downwards, starting from the center of gravity. Now, uniform objects. By uniform objects, we mean objects that have a regular shape, like they are shaped evenly. There are no contours or hollow parts on them. They form a uniform shape all through, such as a uniform rod, a uniform circle. A uniform circle is such that the entire circumference follows the clearly defined path of a circle. There is no hollow part there. There is no contour there. Such objects are uniform. Now, every uniform object has a center of gravity at the midpoint of the object. Every uniform object has its center of gravity at the center, the midpoint of that object. This means that if you have a uniform rod, for instance, and let's say the rod is about 100 meters long, then the center of gravity of that rod should be at the midpoint of that rod. At the midpoint of 100 centimeters is 50 centimeters. So the center of gravity will be at the 50 centimeters. So if you are asked to use an arrow to indicate the center of gravity or to indicate how the weight of the object is, your arrow should start from 50 cm on the object and act or point downwards. A uniform circular object also has the center of gravity at its midpoint. A uniform rectangle or square has the center of gravity at the midpoint also. Now, the midpoint of the rectangle or square is determined by the diagonals. When you draw the diagonal of a square or a rectangle, where they meet, the point of intersection is the center of gravity of that shape. For a triangular plate, the center of gravity is the point of intersection of what we call the meridians. We don't call these the diagonals, we call it the meridians, because a triangle is three-sided shaped figure, and the lines so drawn to determine the center of gravity are not from one tip to the other like we have in rectangles or in four-sided figures. Here, it is from a tip to the opposite side. A tip to the opposite side. One tip of the triangle, the line is drawn straight from there and goes to the side of the triangle facing that tip. And it must be drawn in such a way that it divides that side into two equal parts. So when you do that, for the three tips that a triangle has, where the three lines meet in the triangle, that is where the point of intersection of the meridians is, and that is where the center of gravity of the triangle is. Here we have two diagrams describing positions of center of gravity of some objects. On the right hand side, you can see the triangle I just referenced. The red lines there are the lines of meridians. You will notice that each of the tips, each of the vertices has a line taken off from it and going straight to the opposite side. And it goes to that opposite side so that it divides that opposite side into two equal halves. So you do that for the three vertices. Where the three lines meet in the triangle, that is the center of gravity of the triangle. In case you are asked, a question may give you a triangle like this and say you should identify the center of gravity. All you need to do is to draw those lines of meridians. Where the lines meet, where they intersect, draw your arrow representing the weight starting from that point. For an irregularly shaped object, such as what you have on your left-hand side on the screen, the center of gravity is denoted by that tiny red dot. It is where the line of action of the weight of that object will always pass through. Coming to stability of objects now. When do we say an object is stable? And what do we even mean by stability of objects? When we talk of stability of objects, we are referring to the tendency of an object to topple over when a slight force is applied on it, or to regain its balance. So that is what stability of objects essentially determines, whether the object will topple over or will be able to regain its balance after undergoing a slight displacement. So we have three types of stability. We have stable equilibrium, we have the neutral equilibrium, and we have the unstable equilibrium. An object has a stable equilibrium if it tends to return to its original position after undergoing a slight displacement. So, if I displace an object slightly and it is able to regain balance, it's able to return to its original position, then it is in stable equilibrium. Examples are cones lying on their bases. When a cone is on its base, it's in stable equilibrium. A slight displacement of the vertex of that cone will return the cone to its base, to the position it was in before. Other examples are your iPads and tablets. If you lie your iPads down horizontally on the surface and then you apply a little force on one side to lift the iPad up, once you remove the force, the iPad will fall back to the table. That's that's a stability of objects, stable equilibrium specifically. Now, object stability is affected by the positions of their centers of gravity. So when an object's center of gravity is high, such as in trucks, particularly when the trucks are loaded, they have a high center of mass because the entire weight of the truck and the weight it carries acts from the center up there, as against that of a sport car. A sports car is closer to the ground. Its own center of gravity is closer to the ground. So, a sports car is more stable than a truck because a sports car has its own center of gravity closer to the horizontal, closer to the ground than that truck. So that truck, whose center of gravity is high, if it experiences a slight tilt, it will topple, it will fall over. And that's why you see more falling trucks than you see falling cars. You don't just see a car falling except it is trying to climb a really, really steep slope. But for trucks, any slight tilt, any slight, a truck will run into a pothole and it topples because its center of gravity is high, so it is unstable. Also, objects that have large bases, they tend to be more stable than objects that have narrow bases. When an object's base is large, is wide, it is usually more stable than that whose base is narrow. That was why I talked about a cone lying on its base. The base of the cone is wider than the tip. So if a cone is resting on its base, it is more stable than if it was resting on its tip. Of course, on its tip, it will become unstable because it will fall over. That's an unstable equilibrium. So in stable equilibrium, if slightly displaced, the line of action of the object's weight will still lie within that base. We will see a diagram to illustrate this later. The object in stable equilibrium experiences a moment about its turning point, which restores it to its original position. Now, coming to neutral equilibrium. This occurs majorly for objects that are cylindrical or circular in shape and which roll along the ground. So when an object is rolling on a flat surface, it is in neutral equilibrium because its orientation doesn't change. Even though you roll a ball slightly and the ball rolls along the ground, it goes to rest in a new position. It goes to rest somewhere other than the point from which you rolled it. But it will still remain at rest, still maintaining its orientation. It will still be that circular object that you have. It will not have toppled over, so to speak. So it is said to be in neutral equilibrium. If you roll a cylinder along the floor, it will roll, it will leave its initial position and roll further. But when it gets to its position of rest, it will remain horizontal, remain there lying horizontally. This is contrary to the scenario of the cylinder standing upright. If it was an upright cylinder, and then you apply a force at the top of the cylinder will probably fall to the ground. If the force is high enough, the cylinder will fall. So it has changed position. But when the cylinder is lying on the ground, it maintains a neutral equilibrium. That's it about neutral equilibrium. Now, for unstable equilibrium, if an object experiences a slight displacement and it topples over, then it is in unstable equilibrium. I mentioned the example of trucks, heavily loaded trucks. A slight displacement and they topple over is because they are in unstable equilibrium. Here we have diagrams to just explain the concept of stability of objects. You can see the man. The center of gravity of the man is within his within the space between his feet. So the man will remain stable for as long as the center of gravity lies within that base. So irrespective of the man's position, so far he's still able to keep his center of gravity within his base, it will remain stable, it won't topple. Now, imagine that that man begins to bend to his side, like a goalkeeper, the way a goalkeeper dives to catch a ball. Imagine that that man was a goalkeeper diving to catch a ball. Say he was diving towards his right. As he dives, that red arrow that describes his center of gravity will begin to shift along. As his body shifts, that line will also shift. But as that line shifts, it will continue to point downwards, but it will be shifting out of the man's body. Once it gets to a position where that arrow shifts out of the base between the man's feet, then that man will fall. That man will topple. That's why goalkeepers, once they shift, once they dive, their centers of gravity shifts out of their base, and then they have to fall. So goalkeepers are not just falling because they want to knock themselves on the ground. It's because their centers of gravity have shifted out of their base and they just have to fall. Now, look at the diagram on the right. You can see the truck. Look at the first truck. Its center of gravity is still within that area of support. So whatever force that acts on that truck that tries to push it, so far the truck is able to still maintain that center of mass arrow within its area of support, it won't topple. Now look at the next diagram of the truck. The center of mass has now shifted. That arrow, that red arrow has shifted out of the area of the truck, out of the base area of the truck, and then that truck will fall. You can see it's already on its way to fall. There's no magic that can happen that will restore that truck at that point. It's going to fall. And then the same thing happens to the other diagrams you have on the right. So that is how center of gravity affects stability of objects. Before rounding off, let us look at coplanar forces. Coplanar forces. What do we mean by coplanar forces? When we have two or more forces acting on the same object, then they are coplanar forces. Coplanar. Co means same, similar. Planar comes from the word plane. And when you have a plane, it could essentially be a rod, a tabletop, a flat surface, any object at all could be a plane. So coplanar forces are forces acting together on the same object. Now, coplanar forces could be parallel or non-parallel. Parallel, just as we know of parallel lines are lines that do not meet. So also, parallel coplanar forces are those whose lines of action never meet. Irrespective of how you draw them, if you draw the arrow of the force, the forces lie side by side and they never meet. Those arrows never meet. Those are coplanar forces that are parallel. Now, for the non-parallel coplanar forces, their own lines of action meet. So they are non-parallel, meaning that they can meet. So the lines of action of those forces meet at a point on the object, and then we call them coplanar forces. Here we also have some photographs to illustrate the parallel and non-parallel coplanar forces. If you look at the pictures under the parallel coplanar forces, you see that those arrows will not meet. There's nothing you can do. They will not meet. The green arrow will not meet with the red arrow, and the two red arrows too will not meet. Even if you were to extend the arrows to the opposite side, they still will not meet. So those are parallel coplanar forces. But on the right hand side, you can see the top diagram there. Force A, B, and C are meeting at a point. Those are non-parallel. They are all still acting on that same plane, being that green circle. They are acting at that point, but they are non-parallel because they meet. And right under also, we can see another non-parallel set of forces. That's force FACA, force FABA, and the RA. They are non-parallel. Now, like I said at the beginning of this video, non-parallel forces which keep an object in equilibrium. If they are 3 in number, they are treated as a triangle of forces. So that is why you see that the 3 non-parallel forces there now have a triangle that results from that. So I implore you once again to see the video on triangular forces. It's right on this channel. And please subscribe to this channel so that you continue to get notifications of new and enriching physics videos as you enhance your knowledge of physics and probably prepare for any particular exams you want to take. The non-parallel forces that keep an object in equilibrium, if they are 3 in number, they are taken as the 3 sides of a triangle. The video on triangular forces explains that better. So here is where we will end this lesson. I hope to come across to you with another physics video very shortly, and I implore you to subscribe to this channel and also see the other videos on the channel so that you learn more. You can use the comment box to drop any comments or even make a request. If you have a particular topic you'd like me to do a video on for you, please use the comment box and I'm sure we'll reply. Thank you.